Hey everyone, welcome back to the Bare Metal Embedded Systems Programming from Scratch series. In the last video, we looked at the ATSAM3X8E from a high-level perspective. The architecture, the memory map, the PMC, the PIOB controller, and why the chip needs a proper clock setup before doing anything useful. Today, in this episode, we're going deeper. Because there's a lot to unpack with these registers and addresses, and I want to explain what they do and why we need them, I decided to split this section into two videos. This one is registers and addresses part 1, and in the next video, we'll continue with the rest of the registers. This is the real beginning of ARM Cortex-M3 bare metal programming, mapping the silicon into C code. On Arduino or STM32, you normally use a HAL, Hardware Abstraction Layer, a library that hides the hardware and gives you high-level APIs. But here, we want full control, so we directly access memory map registers using pointers. Let's get started. First, we include stdn.h to get fixed-size integer types, like un32_t, which we need because this microcontroller uses 32-bit registers. So here we say hash include stdn.h. Next, we define the CPU frequency. Hash define f_CPU 84 million UL unsigned long. We'll use this later inside our delay function. Before starting to define registers and bitfields, let's create a simple helper macro. Hash define reg32 inside parentheses ADDR and outside inside parentheses asterisk volatile un32_t asterisk and outside this inside parentheses ADDR. This macro takes a 32-bit memory address and turns it into a volatile 32-bit hardware register. As I explained earlier in the ATmega2560 in C video, the keyword volatile tells the compiler not to optimize this variable. un32_t asterisk, this means a pointer to a 32-bit unsigned value. We're telling the compiler that this memory address should be treated as a 32-bit hardware register. The outer asterisk, this dereferences the pointer. This means instead of working with a pointer, we access the actual hardware register at that address, just like reading or writing a normal variable. But remember, each register has its own rules. Some can only be read, some only written, and some allow both. So dereferencing gives us access, but what we're allowed to do depends on the register itself. Now, let's define the power management controller or PMC registers. These registers control the clock system of our MCU. And a stable clock is essential because nothing on the chip works properly without it. Here we say hash define PMC_base 0x400 E0600 UL. This is the base address of the PMC. You can find it in the ATSAM3X8E datasheet on page 31. The link is in the description below. Now, let's define the other registers inside the PMC. Here's the first one. Hash define PMC_PCER0 reg32 and we pass in PMC_base plus 0x10U. This is the peripheral clock enable register. We use this register to enable the clocks for specific peripherals before using them. Without enabling the peripheral clock, the corresponding hardware won't function. You can find this offset and all other PMC register offsets in the ATSAM3X8E datasheet on page 538 in the table that lists all registers of power management controller. The next one is hash define PMC underscore CKGR underscore MOR reg 32, and we pass in PMC underscore base plus 0x20U. This is the main oscillator register. We use it to configure and enable the main external crystal oscillator, which is the primary clock source for our MCU. Proper configuration of this register is essential before switching the system clock to higher frequencies. Next, we define hash define PMC underscore CKGR underscore PLLA reg 32, and we pass in PMC underscore base plus 0x28U. This is the PLLA register, the phase locked loop A configuration register. We use this one to multiply the clock frequency coming from the main oscillator. In our project, this is what generates the final 84 MHz system clock for the ATSAM3X8E. Next, we define the master clock register. Hash define PMC underscore MCKR reg 32, and we pass in PMC underscore base plus 0x30U. We'll later write to this register to select the clock source and configure the prescaler for the CPU clock. And then we define the status register of the power management controller. Hash define PMC underscore SR reg 32, and we pass in PMC underscore base plus 0x68U. This register lets us check when the clock sources are ready, for example waiting for the PLL to lock before switching the CPU clock. Now we define all the bit fields for the main oscillator register. Let's go through them one by one. You can find all the details about this register in the datasheet on page 546. First, we define the position of the bit that enables the external crystal oscillator. And here we say hash define CKGR underscore MOR underscore MOS CX TEN underscore POS and 0U, the bit 0. Next, we define the actual bit field to enable the external crystal oscillator. Hash define CKGR underscore MOR underscore MOS CX TEN inside parentheses 0x1U shifted left by the position. This means set bit 0 of the MOR register to 1 to turn on the main crystal. We'll use this later when we're configuring the MCU clock. Next, we define the position of the bit that enables the internal RC oscillator. Hash define CKGR underscore MOR underscore MOS CR CEN underscore POS 3U. Then we create the bit field macro that actually sets this bit. Hash define CKGR underscore MOR underscore MOS CR CEN and inside parentheses 0x1U shifted left by the position of the bit. Here we shift 1 by 3 bits to turn on the internal RC oscillator, the built-in clock source inside the chip. We need the internal RC oscillator because it provides a reliable clock source that allows the MCU to start up safely before the external crystal stabilizes. And then we define the position of the startup time field. Hash define CKGR underscore MOR underscore MOS CXTST underscore POS 8U. When you turn on a crystal oscillator, it doesn't start instantly. The crystal needs some time to begin vibrating steadily, like warming up. This warming up time is called startup time or startup delay. This simply tells us that the startup delay value begins at bit position 8. Next is the start time bit field. Hash define CKGR underscore MOR underscore MOS CXTST, and it takes V, then inside parentheses UN32 underscore T V shifted by the position, and inside parentheses 0xFF U shift by the position. Here we pass a value V that will go into bits 8 to 15 of the register. This value tells the MCU how long to wait for the external crystal to stabilize when powering up. We then use the AND operation with the mask 0xFF shifted left by the position. This guarantees that only bits 8 to 15 are affected, and all other bits in the register remain unchanged. Now we define the position of the write protection key. Hash define CKGR underscore MOR underscore key underscore POS 16U. This tells us where the unlock key must be placed inside the MOR register. I'll explain why we need this in a moment, after defining a macro to write that key. And here's the macro. Hash define CKGR underscore MOR underscore key, and it takes V inside parentheses UN32 underscore T V shifted left by the position, and 0xFFU shifted left by the position. The MOR register is protected by a password-like key. To modify it, we must write the correct key into bits 16 to 23. You can find this key in the datasheet on page 546, and this key is 0x37. If you don't include this key, the MCU will ignore any attempt to change the oscillator configuration. Next, we define the bit field to select the main oscillator. Hash define CKGR underscore MOR underscore MOS CSEL underscore POS 24U, and hash define CKGR underscore MOR underscore MOS CSEL, and inside parentheses 0x1U shifted by the position. This bit selects which oscillator becomes the main clock. 0 means use the internal RC oscillator, and 1 means switch to the external crystal. In our case, we'll switch to the external crystal because it's more accurate and stable than the internal RC oscillator, which is important for precise timing and reliable operation of the MCU. Now, it's time to define the bit fields for PLLA, the phase lock loop A. PLLA controls how the main clock is multiplied to generate the system clock, allowing us to reach the target 84 MHz frequency. We'll define each bit field that controls the PLLA input, divider, multiplier, startup delay, and the 1 bit. You can find all the details about this register on page 549 of the ATSAM3X8E datasheet. Let's go through them one by one. First, we define the bit position of the DIVA field in the PLLA register. Hash define CKGR underscore PLLAR underscore DIVA underscore POS 0U. Next, we define the macro to set the DIVA value. Hash define CKGR underscore PLLAR underscore DIVA, and it takes V and inside parentheses uint 32 underscore T V shifted by the position and 0xFFU shifted by the position. This field sets the divisor for the PLL input clock. We need this divisor to reduce the frequency of the main clock before it enters the PLL, because the PLL has a limited input frequency range. If the input is too high, the PLL won't work correctly. Next, we define the position of the PLL count field. Hash define CKGR underscore PLLAR underscore PLLA count underscore POS 8U, and then the macro to set the PLL count value. Hash define CKGR underscore PLLAR underscore PLLA count, and it takes V and inside parentheses uint 32 underscore T V shifted left by the position and 0x3FU shifted left by the position. Here we shift the value V by 8 bits and mask it with 0x3F to ensure only bits 8 to 13 are affected. This field sets the PLL startup delay. It tells the MCU how long to wait for the PLL to stabilize before using it as the system clock. Next, we define the position of the MULA field in PLLAR. Hash define CKGR underscore PLLAR underscore MULA underscore POS 16U. Now the macro to set the multiplier value. Hash define CKGR underscore PLLAR underscore MULA, and it takes V inside parentheses uint 32 underscore T V shifted by the position and 0x7FFU shifted by the position. Here we shift the value V by 16 bits and mask it with 0x7FF to ensure only bits 16 to 26 are affected. This field sets the PLL multiplier, which determines how much the input clock is multiplied to produce the PLL output frequency. By adjusting this, we effectively increasing the system clock frequency generated by PLLA. Finally, we define the 1 bit in PLLAR. Hash define CKGR underscore PLLAR underscore 1 underscore POS 29U, and hash define CKGR underscore PLLAR underscore 1 inside parentheses 0x1 U shifted by the position. Shifting 1 by 29 sets this bit when we write to PLLAR. The 1 bit is required by the MCU. It must always be set to 1 when we configuring PLLA. Otherwise, the PLL will not work correctly. Alright, that wraps up registers and addresses part 1. Today, we build the foundation, mapping the PMC and CKGR registers, breaking down every bit field, and understanding why these values matter for getting the ATSAM3X8E running exactly the way we want. In the next episode, we'll continue with the remaining registers and move on one step closer to getting the system clock running at full speed, completely bare metal, no libraries, just pure control over the hardware. If you are enjoying this deep dive into bare metal programming, make sure to hit like, subscribe, and turn on notifications so you don't miss part 2. Thanks for watching, and I'll see you in the next one.